And so, well, clearly I'm not understanding. If I was under standard conditions, then I know the pressure already. The pressure would have to be 1 bar. And so is this allowed? If I have my delta G at 50 degrees C, I can calculate my delta G at 50 degrees C under standard conditions, because the delta G at 50 degrees C is going to be delta H at 298. So we'll assume at 298 Kelvin at 50 degrees C is close enough, minus T delta S at 298 under standard conditions. But is it okay to do this? Because now I can do this calculation because I know the temperature. Temperature is going to be 323 Kelvin. I got my delta H from the board data. I can get my delta S from the board data, and I have that. But that's delta G under standard conditions, and the pressure is not going to be under standard conditions. So is it okay to use it? And the answer is, can I use this equation? Seems like no, because, you know, if you're dealing with a real gas, should you be using the ideal gas law? Probably not. You should be using the real gas law, like Van der Waals. If I'm under non-standard conditions, is it okay to use standard conditions? Yes? The answer is yes. The answer is yes, because I'm not under standard conditions. This delta G means I'm not under standard conditions, right? But the way I calculate it is I reference it to standard conditions. And so I apply a correction to standard conditions in the form of RTL and a Q. And so yes, I'm going to use it under standard conditions, but I'm not at standard conditions, because this delta G is related to this, which we're going to correct. Does that make sense? And so then it's okay. And so I'll just calculate my delta G 50 degrees under standard conditions, plug that in here, divided by RT, and then calculate my pressure. Or I can plug it in up here. And so this is doing it there's two separate calculations, or I can combine it into one. You know, if I combine it into one, then it could look something like this. You know, for example, K is equal to E to the minus delta H naught minus T delta S naught over RT. This works here because then I can assume that delta H at 298 and delta S at 298 are okay, and then have the temperature at 323. So either of those will give you the same answer, because it's basically doing the same thing in 2 steps or 1 step. All right. Does that answer your question, Eric? All right, any other questions?
Number 1 is C.
Number 1 is C. Delta G value equal to 0 kilojoules per mole means that when the system reaches equilibrium, K will be equal to 1. Is that true? Unfortunately, it's not true. Let's look at an example here of why it's not true. Let's say here, delta G has reached equilibrium, right? This is going to equal delta G naught plus RT ln of K. Now, if K equals 1, right, then this whole term equals 0. But delta G naught is 8.5 kilojoules. If delta G naught is 8.5 kilojoules, then does that make sense? Like, if delta G is equal to 0 in this particular reaction, does that mean that K is equal to 1? No. No. What you're thinking is delta G naught. If this were a delta G naught value equal to 0, when delta G naught is equal to 0, then K is equal to 1. But not delta G. Okay, other questions?
So the answer is
So the answer is not B, because B, if the gases are 1 atmosphere and the solutions are 1 molar, then K is equal to 1. It's got to be D.
why has it tricked us?
Why? Because delta G and delta G naught are confused all the time, and so people don't really know the difference that well.
So you're saying that delta G naught is the corrected form of delta G? Standard condition.
No, delta G is the corrected form of delta G naught. You correct delta G naught to get delta G by this calculation. That's one way of doing it, unless we already knew what delta H and T delta S were. If we knew what delta H and T delta S are under non-standard conditions, and they're the same as this, then we can get it without correcting our standard condition. But the way we do it typically is we just correct the standard one. And so even though we're under non-standard conditions, standard conditions will play a role because that's how we calculate it. We aren't typically given this. We compare everything to the standard condition. In other words, you start off at a Q of 1, and then how far away are you from equilibrium? You know, that's what we're going to get from the K value. Okay, other questions?
Number 6.
Number 6 on this test? No, homework. I was thinking. Number 6 on the homework. I'm not sure if I signed it. For the reaction, methane plus 2O2 yields CO2 and water. Select all the following quantities that will always be the same number, 298 Kelvin, no matter how the combustion of 1 mole of methane gas is carried out. Heat. Is heat always the same no matter how you combust something? No. Heat isn't. Heat is what we call a path-dependent function. This is from chapter 7. A path-dependent function depends on how you carry out the combustion. So, for example, if you carry out the combustion to warm up a pot of water, you'll get a certain amount of heat, versus if you carry out the combustion in a CNG car, like a compressed natural gas car, you'll convert some of that energy into work, not all heat. And so if we heat up a pot of water, all that energy is converted into heat. If we burn it in a methane vehicle, a lot of that energy is converted into work, and we get less heat as a result. So it's not A. Delta G. Is delta G always the same no matter how you carry out the reaction? No, I mean, if you change the concentrations, that changes Q, which changes delta G. So, you could do it at different concentrations, you can change it. Different temperatures will change it. Different pressures will change it. So delta G depends on how the reaction is carried out. But it's different. Once you fix those conditions, then it's always the same. How about delta H? Delta H, we're assuming, doesn't change much, but it does change a little bit. So delta H depends on how you carry out the reaction. Right? Although, this is tricky because delta H is a state function, and we made it into a state function so that the energy output is always the same. And so when I say this, as long as the conditions are the same, we're always going to get the same delta H. As long as the conditions are the same, we're always going to get the same delta G. But if we start changing those conditions, then that's going to change. How about delta G naught? Does that quantity stay the same, or does it change depending on how you carry out the combustion?
Change.
It changes?
Temperature?
Well, the temperature is fixed at 298 Kelvin.
Oh, no.
Then no? Yeah. Yeah. So for example, if I carry it out at a different Q, at a different concentration or a different pressure, I'll get a different delta G, right? If I carry it out at a different concentration or different pressure, I will get a different delta G. Huh? But delta G naught, am I allowed to change the pressure? No, because the pressure is fixed at 1 bar. Am I allowed to change the concentration? No. And so it never changes. Delta G naught never changes because the concentration and the pressures are fixed. Whereas delta G changes because the concentrations and the pressures are not fixed, and they can change, and you can input that as Q in the equation. Okay. And so delta G naught doesn't change. How about delta S naught? It's the same thing. It doesn't change because you're fixed, you're restricted. Whereas these ones, you aren't restricted. You can, but these ones it's tricky because these ones are still state functions. This is a path-dependent function, so it's a little bit different. Delta H doesn't change as long as you anyway.
It'll be D and E then.
It should, yeah, D and E.
Delta H doesn't change as long as what?
Well, as long as the pressure doesn't change. But delta H will change depending on the pressure. If it's at standard pressure, you might get a different delta H than, let's say, half an atmosphere, or 2 atmospheres, or 2 bar. So we don't know if it's fixed or not.
You know 5.
Okay, what temperature did you calculate for number 5?
So I used the equation.
Well, this one we could see, if delta H is endothermic and delta S goes down, then, both driving forces are unfavorable. And so we call that non-spontaneous at all temperatures. We can see that it's non-spontaneous at all temperatures by trying to change the sign of delta G. If we tried to change the sign of delta G naught, we said delta G naught equal to 0, which is equal to delta H naught minus T delta S naught. And so we're trying to pass through a 0 point because right now it is non-spontaneous. So we can solve this for temperature. Temperature is going to equal delta H naught divided by delta S naught. Delta H naught is given for us as 450 kilojoules, 450,000 joules. The delta S naught is 200 joules per Kelvin, negative. The joules cancel, it gives us Kelvin, and what do we come up with for temperature? Yeah, we come up with negative 2,250 Kelvin. So that's where it's going to transition from positive to negative, right? And so in this particular reaction, we have a positive delta G. That is, it's because we have plus 450 kilojoules here, and then we have a delta G equals delta H minus T delta S. So we have T, and then delta S is 200 joules, so it's 0.200 kilojoules per Kelvin. So at 298 Kelvin, this is positive. So delta G is positive at 298 Kelvin. What we want to figure out is how can we make this negative? We can make it negative by increasing the temperature. So well actually, how can we make it negative? We can't increase the temperature. We have to, decrease it. If you decrease the temperature, eventually what I can have is these two terms cancel out. That's when delta G naught is equal to 0. The delta H term cancels out with the T delta S term. And that temperature is 2250 Kelvin, negative. And so I just have to cool this down to negative 2250 Kelvin and lower, and then this will go from non-spontaneous to spontaneous. All right, there's a problem with that. What's the problem? Yeah, the lowest I can go is 0 Kelvin. That's when all motion stops, right, except for electron motion. And that means this is an impossible temperature. This is an impossible temperature, therefore it's impossible to make this reaction, whatever it is. It's impossible to make it spontaneous. And so what we say is it's non-spontaneous at all temperatures, because all the temperatures are going to be from 0 on up. And that's going to be covered by this. Okay. Number 3. A mixture of air and methane reacts very slowly at 298 Kelvin because delta G naught is close to 0 at this temperature. Is there a driving force for methane reacting with oxygen? Yeah, I mean, if I fill this room up with methane gas and there's oxygen here, I'd be worried, right? Because there's a pretty big driving force. But at room temperature, I don't worry that much because I'm not going to have a fire here at room temperature. I'd have to have a spark or some other hot surface to come in contact. And so it reacts very slowly because delta G naught is close to 0. No, delta G naught is quite negative. It's highly favored, this reaction. It reacts very slowly at 298 Kelvin because delta G naught is highly positive. No. It reacts very slowly at 298 Kelvin because delta G naught is highly negative at this temperature. And so the best answer for this would be well, if you look at the answers, this brings up the difference between thermodynamics and kinetics. Kinetics tells us how fast the reaction goes. Thermodynamics tells us the driving force. Typically, something with a strong driving force or powerful driving force reacts quickly, but not always. And so this is a situation in which it's like none of the above. You know? It reacts very slowly because of other factors, not because of delta G.
Which factors
It reacts very slowly because of the Boltzmann distribution at room temperature. The activation energy is fairly high. So the population of molecules with enough activation energy is small. It's burning, but it's burning extremely slowly. It's like paper. If you look at an antique book and you look at the pages of paper, they look like they've been charred by fire. Have you noticed that? They're all brown and they look like they've been burned. And in fact, they have been. They're being slowly oxidized by oxygen in air. And so a lot of documents, they don't store in the presence of oxygen, they store it in the presence of other gases. And so it's none of the above. The mixture reacts very slowly because it's metastable. The activation barrier is too high. When the activation barrier is too high, the population is small for reaction. One way we can get the reaction of methane and oxygen is immediately when I open this, methane and oxygen are going to start to react, just not very fast. But one way to do this reaction a lot quicker is to increase the temperature. So if I had a hot surface, I can ignite it, or a match, I'd be able to ignite it. Okay. Once I ignite it, this reaction is so exothermic that, let's say the activation energy is like this. This reaction is so exothermic that the energy released in the reaction will help heat up the remaining reactant molecules, speed them over the hump. Okay, other questions from this?
What does P7EXT mean?
External pressure. That would be like barometric pressure or atmospheric pressure. And the reference is for boiling. When boiling occurs, the external pressure is equal to the vapor pressure. Okay, any other questions? No? Number 11. The Haber process synthesizes ammonia from the elements. Why do I have two different exams? Somebody showed me an exam earlier. That's all right. Yeah, someone gave me a copy of an exam earlier. All right. So we're synthesizing ammonia from the elements, nitrogen and hydrogen. So we need to balance this equation. We need 2 nitrogens and 2 ammonias. Or no, that's not right. Sorry. 1 nitrogen, 3 hydrogens, and 2 ammonias. They're all gases. At what approximate temperature will a mixture of 1.00 bar nitrogen and 1.00 bar oxygen be 90% converted to NO gas. And so when we think about 90% conversion to NO gas, 90% conversion means 90% reaction to NO gas. That's how I'm going to convert it into NO gas. And so if I have 1.00 bar here, and 1.00 bar here, and 0 bars here, I have to figure out what is my limiting reagent. Can you just do the limiting reagent by sight? What would the limiting reagent here be? Would it be H2 or would it be N2? It'd have to be H2. Because if I have one N2, I'm going to need 3 H2s. I only have one H2. And so H2 must be my limiting reagent. And so I'm going to lose 90% of that. This is 90% converted. So you lose 90% of this. 90% of 1 is how much? 0.9 bar. And so I'm going to be left with 10%, which is 0.10 bar from an initial of 1. So if I lose 0.90 bars, then I'm going to lose 1/3 that, right, for nitrogen. And so for nitrogen, it's going to be minus 0.30 bar. And then I'm going to gain 2/3 this. Well, 2/3 of 0.60 bar. And so here, 1 minus 0.3 gives me 0.70 bar. And 0 plus 60 gives me 60 bar here. And so this would be my 90% conversion using an ice table to do this. And then I want the reaction to stop. If I want the reaction to stop here, then I got to make sure that Q is equal to K. So initially Q is not equal to K because I got a 0 here, so Q is much smaller than K. But what I wanted to do is I wanted to react such that Q is equal to K at this point. Here Q is going to be 0, which is going to be less than K. And so that's my desired K value. At what approximate temperature will the mixture, okay. And so the K value that I want, and so we need this K value for this problem to work. It's going to be the ammonia squared, so this is going to be 0.60 squared, divided by the N2, which is 0.70, divided by the H2, which is 0.10. And so this is going to be 0.10 cubed. This is the K value that I want. So what does it come out to here? $514? Okay, we want a K value of 514. It turns out K at 298 is actually quite small. This is not a favored reaction. And so the temperature of 298 Kelvin won't work here, so we got to figure out what the temperature is. That'll give us a K equal to 514. So take a look at the reactions that we've covered and see, not the reactions, but the equations that we covered, and see which one would be appropriate for this particular problem. Be right back.